Hi all, I'm Meghamala, working as an assistant professor from Institute of Aeronautical Engineering. So today's topic is about the analysis of synchronous sequential machines part 2. So here in the last section we have discussed about synchronous sequential machines. What are the synchronous sequential machines? Basically, what is a synchronous machine and the difference between the synchronous and the asynchronous sequential machines. And we all discussed about regarding the things pertaining to the synchronous machines. And now we will discuss about the part 2 of the same continuous topic, synchronous sequential machines. So coming to the general model. So here in the general model, we say that every machine, it has the current state at the time, next state and the outputs at time. So here in the general model, in the general figure, we can say that the current state at time T, the time T is stored in any flip-flops. So in the array of flip-flops. So coming to the flip-flops, as I said, your flip-flops are nothing but the storage elements. They store one bit of information. They just store the data where the current state of that particular flip-flop, it has a time T, and that the time T that will be stored in the array of the flip-flops. And then coming to the next state. So soon after the current state, the next state will be the time T plus 1. So for this time T plus 1, it's nothing but it is a Boolean function of states and state and the input as well. So here the next time, previously the time would be T, and now this time, for the next time, the time will upgrade to T plus 1. So here in this T plus 1, the Boolean states of a Boolean function of a state and inputs. So here in this, the next state at time T plus 1, we see the Boolean functions in terms of the states and as well as the inputs. And then output. After the next state, soon after the next state, we'll go to the output state. The output state, the time is recorded at T, and it is for a Boolean function of state T and melee of inputs. So here in the output it defines with respect to the time T, and this output is accommodated with the Boolean function and as well the machine that you are considering. Is it a sequential machine or else the combination of machines? So basically, compared to the combination, we'll go with the sequential machines. So in the sequential machines, in the last class, we have discussed about two kinds of machines we have discussed about, that is a melee and more. These two are the basic sequential machines. And now, if you observe this particular diagram, block diagram, we see here the combination logic circuit, and for this we have the inputs and the outputs, and then followed with the next state. See, this is nothing but the storage elements. So this storage elements, we can say it's a flip-flop, latch, okay, whatever it is, the elements which stores the bits of data. So here in the example, we are considering the flip-flops as a storage devices. So here, this is a storage elements, and the input of the storage elements is nothing but the combinational logic input, and soon the output can be considered the next state logic. Okay, so if you observe here, the combinational output is nothing but the next state logic, which is given as or else it acts as one of the inputs to the storage elements. And then for each and every storage elements, that means if you are considering any flip-flop at latches, remember that the clock is to be given, okay, based on the positive edge or else the negative edge clock. If it's a positive edge, it goes from 0 to 1, and if it's a negative edge, it falls from 1 to 0. So for each and every storage elements, we have a clock input, and then it is accommodated or else it is in relation with the combinational logic circuit. So this is just about the understanding of how a sequential machines work along with the combinational circuit. And then we'll move on to the examples. When it comes to the analysis part, we see the code can be written in terms of the input x of t. My input is x of t and the output is y of t, and states. Okay, two states that I can consider, that is a of t and b of t. So the state, see, each and every state have the state register. So this state register will store the information that that particular state is holding. So the state consists of the input a of t and b of t, and the output is x of t and as well the y of t. And then what is the output function? So in case the Boolean expression, we say the next state will hold the Boolean expression, right? So we have the present state, next state and the output. Always the next state, it holds the Boolean expression. So what is this Boolean expression or the function? So Boolean expression is nothing but it is a combination of the output with respect to the input. So here the output is y of t. Y of t is the output, so it's the output of y of t. Y of t is nothing but the input x of t into b of t plus a of t. So x of t is nothing but the input along with the states. Inputs along with the states. So x of t into b of t plus a of t. We know that this b of t and a of t are nothing but the states. Okay. So the output is nothing but it is a combination of input as with respect to the states. And then what is the next state function? So this is a output function. Output function, this is how we can write in terms of input and as well as the state. And then if we go forward, the next state function. The next state function is nothing but the next state. Always remember the next state, the time goes with t plus 1. The present state time goes with the t, and as well the output, the time goes with the t. But when the transition taking place from one state to the another state, that is a present state to the next state, the time period goes with respect to t into t plus 1. Okay, so now we will see the function of the next state. The next state function can be given as a of t plus 1, which is equals to a of t into x of t plus b of t into x of t. And then b of t plus 1 is nothing but a of t into x of t. So here, if you observe the next state of the present state too. So this is my present state, and to this present state, my next state would be b of t plus 1. And if it is a present state a of t, my next state would be a of t plus 1. So for this, the output function can be written as a of t plus 1 is nothing but x of t into a of t plus b of t into x of t. Okay, that means what? X of t is nothing but the input, and a of t and b of t are nothing but the states. These are the states, right? So for b of t as well, as b of t is another state, we can write the next state of that present state b of t as b of t plus 1, and then the output of that particular b of t plus 1 can be written as a of t into x of t. So this is a general understanding regarding the state with respect to the input and output, and that is also with respect to the present state and as well as the next state. So this is a simple analysis based on a given example. So we have a simple example as input and output as simple coefficients as x of t and y of t, and the states as a of t and b of t. And here this is just a general analysis of the output and with respect to the next states. Okay, so this is a Boolean expressions with respect to the output function, and as well as these are the Boolean expressions with respect to the next state functions. And coming to the state table analysis. So here is the synchronous sequential circuits or asynchronous sequential circuits. Okay, whatever the sequential circuits that you are considering, always remember that a particular machine should have a state. Okay, that machine should have a state, then state table. Okay, and then state table and state function and state register. Okay, so what is a state table characteristics? So here we can see some characteristics pertaining to the state table. So state table is nothing but it is a multiple variable table. It is a multiple variable table with the following 4 sections. So here in the state table, we see it is of 4 sections. It is comprised of 4 sections where a multiple various table. This table is nothing but a multiple various table with the 4 sections. So first one is present state, input, next state and the output. So these are the 4 sections that we can see in the next state or else a state table. In the state table, we can see the 4 sections. They are nothing but present state, next state and input and as well as the output. So what is this present state? Present state is nothing but the values of the state variables of each followed state. So if you are in a present state, okay, if you are in a current state, so that current state will hold some data, will hold some the address bits or else the information, right? So the value whatever the present state is holding, the current state, the value whatever the current state is holding, then that is nothing but the present states. So the value of this state variable for each allowed state. So for example, my states are A, B, C and D. So these are the states, and I am calling A as a present state, B as a next state. So here present state is nothing but, so this all the states are holding a data as 0, 1, 1, 0, 1, 1 and 0, 0. So this is the data where all the states are holding. But as per my knowledge or as per my perspective, I am saying that present state A is holding some value that is 0 and 1. Okay, so this is a 0 and 1, and why? Because this is a present state to my extent. And then if I'm considering another state D as a present state, what happens is now D will become the present state where it is holding the information as 0, 0. Okay, so here the present state states are the value of the state variables for each allowed state. Okay, so this is a value that is that respective state which is holding. So the value of the state variables for each allowed state. Sometimes I may allow this as a present state, and in the next scenario I can go with this D as a present state. So that's the reason we are saying that the values of a state variable for each allowed state. And then coming to the next category or else the next section is a inputs. So what is this input? The input combinations allowed. So here each and every state will have some input state and input values and as well as the output. So the input is nothing but the input combination. The combination with respect to the present state is nothing but the input. So the input combination which is allowed is nothing but the input. And then the third one is, the third section we can see here is, in the state table we see here is the next state. So what is the next state? The value of this state at a time t plus 1 based on the present state and the input. So here my next state here as per the example that I have considered is, I have 4 states A, B, C and D. So here in this A, B, C and D states, my present state, the current state is A. A would be my current state and the next state is B. So here what is this next state holds? It holds a value of the present state and the input. So whatever the input that is carried out with respect to the present state, it holds the present state and the input, and as well here the time will change as t plus 1. Why? Because here my present state value holds a time as t. When the transition is taking place from one state to another state, the time transition increases. It increases to t plus 1. So that's how I say the next state, the value of the state at time t plus 1 based on present state and the input. So this next state, it always holds, or else it will have in relation with respect to the present state and as well as the input. But here the time constraint would be changed from t to t plus 1. Okay, the present state always, that before the transition the time goes with t, whereas after the transition the time goes with t plus 1. And then coming to the output. What is the output here? The value of the output as a function of present state and the input. So here the output of this particular state transition is nothing but always the output holds the value of the present state and as well as the input. Okay, so here we can say that state table consists of 4 sections followed with the input, output, next state and the present state, and each and every state will hold a value with respect to the time constraint. Always remember, the present state holds the time with t, whereas the next state holds the time with t plus 1. And then from the viewpoint of truth table, okay, so in general, from the general points of the truth table, we can analyze that the inputs are input present state. So the inputs can be inputs and as well as the present state, and the outputs are output next state. Always, if this is a particular state, the input will be present state and the inputs, whereas the output will be next state and the output. Always output drives towards the next state, whereas the present state, it drives the input and as well as the present state. So this is a general viewpoint of a truth table. For each and every truth table, we can write the transition, how the transition is taking place from the present state to the next state. If it is followed with the next state, and obviously we can say that it is the output state. Okay, output state always accommodate or else it accompanies with the next state, whereas the present state, it goes with respect to the input or the present values. And then coming to the state diagram. So what does the state diagram talks about? The sequential circuit functions can be represented in graphical form as a state diagram. So here the circuit functions, the sequential functions or the functionings of the circuit, particular circuit, sequential machines can be represented in the graphical form or else in terms of the state diagram. Okay, so using the state diagram, we can easily analyze the transition or else the transitions between the different states. Okay, so here in the state diagram, you will be observing the circles. Okay, a circle with the state name in it for each state. So here each state will have a circle. Okay, that means what here? My state A, my state A. That A is in the circle. So this is nothing but the state. Then a directed arc from the present state to next state for each transition. So here, if the transition is taking place from present state to the next state, then it will be directed with an arc. So that's how the representation. So my present state is A and my next state is B. So here, if the transition is taking place from A to B, then the direction can be given as a simple arc. Okay, so here this transition from state A to state B, that is from present state to next state, can be directed from the arc, directed with respect to the arc. That shows that the transition is taking place from A to B. For suppose if you see A and B like this, in this way if you observe, then here comes that the transition is taking place from B to A, that is from state B to state A. So here in this particular example, I can say the state B as present state and state A as next state, isn't it? Then a label on each directed arc with the input values which causes the state transition. And so here we will see some labels. So that labels would be in terms of one each circle with output value produced Moore type and one each directed with the output value produced Mealy type. So here Mealy and Moore, these are nothing but the sequential circuit examples. So these are the sequential machines, whereas in Moore type we see the on each circle with the output value produced. So here on each and every circle we see the output value which is produced. So this is, if this is an input value, then this is the output value. So such kind of directed or such kind of diagrammatical representation can be observed in the Moore type. But whereas in Mealy type we see on each directed arc with the output value produced. So on each directed arc, see for example, my transition from A to B is 0 and 1. So here what happens is 0 is the input and 1 is the output. That means what? When the state is taking transition from A to B, the output that is getting with respect to the present state or with respect to the output next state is 0, 1. 1 is the output. So on each directed arc with the value produced. So such kind of thing is nothing but the Mealy sequential machines. So in the Mealy sequential machines, on each directed arc, we see the output value is to be given. Okay, the output value is to be produced. So this is a general understanding between the Mealy and Moore and Mealy and more type sequential circuits. So in the state diagram, we see the circle, we see the directed arc, and we see the labelings of the input and as well as the output. Okay, so this is how we represent. Labeling can be done by 1/0 or 0/1. This is nothing but the labeling. So before slash is nothing but the input, and after the slash is nothing but the output. And in the state diagram, we see that each and every state can be accommodated in the circle. If something, if some value that you see, or else if some number, or else if some name that you see inside the circle, it means that it is a state. And the transition, if it is taking place from one from one state to the other state, then that kind of representation can be given with respect to the directed arc. Okay, so this is about the state diagrams. And coming to the example, in the example, this is an example, a simple example. Through this example, we can understand the state table and the state diagram. Okay, so state diagram gets confusing for large circuits. So this is a simple example that I am considering, but basically when you are designing for complex designers, okay, for complex circuits, you see the diagram would be more complex. For small modules, diagrammatical part representing in the representing part will be very easy, but whereas for the complex circuits, the diagrammatical part is bit difficult to analyze and to understand as well. So this is a small example that I am considering. So here in the small circuit, it's usually easier to understand than the state table. So here, as I'm considering a very small example, in the small example, it's very easy to understand the state table and as well as the state diagram. So here we have A and B. So A and B are the two states. So A plus is AX plus BX, and B plus is with respect to the AX, and the output is X of both A plus B. Okay, this is the state. A and B are the two states. Two state, and Y is the output. So my output is the combination of X into both the states, B plus A or A plus B. And IO is nothing but it's a labeling. I said right, in the state diagram, we see the labeling. See, this is nothing but the labeling. Labeling. That means what? We are labeling the input and as well as the output. So here, 1/0. It means what? 1 is the input and 0 is the output. As I said you here in this example, for example, this is the 0 is the input and 1 is the output. So here, this is how we represent the states and the outputs, and also the labeling of the input and as well as the output. So coming to the state table. So here in the state table, we see the present state. Okay, present state, next state, and the output. So here in general form, the sequential machines, in order to the implementation of the sequential machines goes with the three categories. First one is present state, next state, and the output. So here in this figure, we see A and B. So we see the four combinations: 0, 0, 0, 1, 1, 0, and 1, 1. So here, if you observe, my two inputs are 0, 0. And when the transition is taking place, see here, A and B as 0, 0. When the transition is taking place from 0, 0 to 0, 1. See, 0, 0 to 0, 1. Next state. So here when X is equals to 0 and X is equals to 1. So my next state here, I can take X as 0, one state, and X as 1 as the another state. So when it is from 0, 0, A and B, it is taking its transition from 0 to 1. So 0, 0, 0 to 1, when X is equals to 0, what is the output? It would be same 0, 0. Okay, but when X is equals to 1, so when X is equals to 1, it is taking place from 0 to 1. If it is 0, then it is in the same state, present state, current state itself. But when it is, when X is equals to 1, then the transition is taking place from 0 to 1. Okay. And then output, if we observe, when x is equals to 0, my output would be 0 itself. Okay. So when x is equals to 0, my output is 0. But when x is equals to 1, my output is also 0. Okay. So this is a next state with respect to the A as 0, 0 present state, and this is a next state. In two scenarios, we see input as 0, x is equals to 0, and for x is equals to 1, the output is 0. Okay. And then coming to 0, 1. So when 0, 1, if 0, 1 is my present state, what happens here? The next state would be when x is equals to 0. See here, when x is equals to 0, for 0, 1 case, when x is equals to 0, we see the output is 0 and 0. But when x is equals to 1, when x is equals to 1, what happens? It's taking its transition to 1, 1. Isn't it? When x is equals to 1, it's taking its transition to 1, 1. But when x is equals to 0, it is in the in itself. Okay. So the state is in itself as 0, 1, 0, 0. So it is 0, 0. And then if it is taking transition, then the output is 0. So my x is equals to 0 when output is 1, and x is equals to 1 when the output is 0. So likewise 1, 0. And now this is my present state. If the present state, when x is equals to 0, when x is equals to 0, what my output? My output is 1, 0 itself. Okay. But whereas here the output is 1. Output is 1. Input and output is 1. And then it is 0. So last case, if you observe 1, 1, this is my present state. And if the state is transition taking place to 0, 0, then my output will become x is equals to 0 as 1. See, x is equals to 0 as 1. Whereas x is equals to 1, for x is equals to 1, my output will become obviously 0. So whatever the state 1, state 2, state 3 and state 4, whatever the states that you are considering, remember that each state will take its transition itself for one time, and then the transition goes with the other time. Okay. And that's how the transition between the different states goes on like this. This is all about the state diagram and state table. State table consists of next present state, next state and output. And with respect to the state table, we can draw the state diagram easily. So for simple designs, the state drawing the graphical representation is very easy, whereas for complex designs, the graphical representation is more difficult. So now we'll see the analysis with JK flip-flops. As I said you, in the sequential machines, the storage elements. So the combinational circuits are considered with the storage elements. So these storage elements, it could be of flip-flops, latches. So when you are considering the flip-flops, in these examples, in order to analyze the state table and state diagram, I am just considering the JK flip-flops. So here we will see the JK flip-flops. This is a JK flip-flop, and here is X is the input, A and B are the output. So JA. Okay, so what is this JA? My output would be B, and for JB, my output would be X. So here for JA, we have J and K. So for KA is nothing but the, so this KA I'm given to, this KA is given to as K, and clock is, common clock is given to for both the flip-flops. And here you can observe the J is given as the output of one flip-flop is given as the input of other flip-flop. So here my JA would become is equals to the output B, and one JB will become the output X. Whereas here KA, okay, the KA is nothing but, it's nothing but the output of one is given as the input of the next flip-flop. So it becomes BX bar, and KB is nothing but the A bar X. See here, This is all about the expressions we are writing with respect to the gates that you are presenting. So Ka is nothing but Ax bar. Okay, so this is A bar x plus Ax bar, that is A XOR B. A XOR X. So here you can observe the state analysis with JK flip-flop. In this particular state table, we see that the present states have the 8 combinations with respect to 0, 0, 0, 1, 1, 0, 0, 0, 0, 8 combinations of both the states 0, 0, 0, 1, 1, 0 and 1, 1. This is 0, 0, 0, 1, 1, 0 and 1, 1. And here, when it comes to the input, the present state input always goes with 0, 1, 0, 1, 0, 1 and 0, 1. And now we have to see the next state. So the next state will goes with respect to the specified flip-flops input. Sometimes we may see as per the diagram that we have seen the previous one, there we have seen a NOT gate, okay, and there we have seen the AND gate, and also we have seen the XOR gate. Okay, so based on the Boolean expression, we can able to draw the circuit diagram. Okay, so now the circuit can be specified the flip-flops input equations. So these are the input equations. As I said, A and B are the two states, and these two states will followed with the JA bar plus K bar A, which is equals to BX, and the next state it only has JB bar plus K bar B. Okay, so these are the two expressions with respect to the two states A and as well as the B. So now substituting JA and JB from the input equations, so we will be getting the A, one of the input A as BA bar plus B bar X bar A. That is, we can see here the AND gate, we can see here the XOR gates, and also we can see the OR gate, right? And or XOR as well. So the state equation, this is a state equation. Okay, so the state equation, it provides the bit value for the column under the next state of A in state table. So here in the state table, if you observe this state table, all this the expression whatever we got with respect to the A state. So this is what we got with respect to the A state. So here the expression, it provides the values, okay, the bit values. It provides the bit values and the expression for B. So this is a state A and this is a state B. So for B state as well, we will be getting the bit values, okay. We will be observe the bit values which can be derived from the characteristic equation by substituting the value of JB and KB. So for substituting value of JB and KB, we can easily find out the Boolean expressions for these two states A and B, whereas finally after substituting the values, we can dump the values over here such that we will be obtaining the next state values. Okay, so we can see here clearly the state diagram of sequential circuit. So this is a state diagram of circuit. Here you can see the two expressions with respect to the state inputs A and B as B A bar plus Bx bar B. So you have to substitute all the combinations 0, 0, 0, 1, 1, 0 and 1, 1 over here in the expression. So finally, after substituting the expressions over here in this, we will be obtaining the values as well for the next state A. And similarly for B state, after substituting all the values 0, 0, 0, 1, 1, 0 and 1, 1 over this expression, we will be obtaining the values in the B category, B state. That's how we can easily get the next state values. So this is just an analysis of example based on the flip-flop. And now we will see the equivalent state definitions. So what is this equivalent state definitions? Two states are equivalent if their response for each possible input sequence is identical output sequence. So here the name itself is talking about the equivalent state definition. So what is this equivalent? If two states A and B are equivalent, that means what? Each possible input sequence is identical the output sequence. So that's how we are saying that these two are the equivalent state diagrams. Each possible input statements of a particular state must be equal with respect to the each possible output sequence of that particular state. And then if these two states are balancing each other, then we are saying that it is a equivalent state definition. So alternatively, we can see that two states are equivalent if their outputs produced for each input symbol is identical and the next state for each symbol are same or equivalent. So this is a small example or a small explanation for the equivalent. Here we are saying that if we have two states A and we say that the output which is produced by each state, each input must be identical, must be the same with respect to the next state for each input symbol or the same or equivalent. Okay, and then two states are not equivalent or distinguishable. If two states are not equivalent, that means what? The inputs are not obviously observed with respect to the output sequences, then it is nothing but the distinguishable states. If both are equal, then we are calling it the equivalent state. If not, then we are calling it as the distinguishable states. So this is an equivalent state example. This is a small example where we see for each state S3 and S2. So here S2 and S3. So for each state S2 and S3, the output for input 0 is 1. So the output for input, this is the input, this is the output. So we are talking about state 2 and state 3. So for the state 3, we have 1, 0. Okay. State 2, 1, 0. And for state 3, the next state for input 0 is S0. So input 0, this is my input. This is my output. So the next state for input 0 is S0. So this is my input 0. From S2, my input is 0 such that the state is taking transition from S2 to S0. Isn't it? So from S2 to S0, the transition is taking place with respect to the input when it is 0. And then input 1 is S2. So if it is input 1, this is input 1, right? If it is input 1, then the state is being itself S2. If input 1, then it is in S2. If input 0, then the state is taking its transition to S0. That is what the equivalent state saying about the next state. Okay, the next state for input 1 is itself is S2, whereas for input 0, the next state is S0. And then state S3 and S2 are equivalent. So now we can see, now if you observe S2, state S2 here, we have seen input as 1. When the input is 1 and output is 0, this transition is taking place to S2, and one more transition when input is 0 and output is 1, then the transition is taking place with respect to S0. So here we see S2 and S3. The S2 taking transition with respect to S0 and S3 taking transition with respect to S0. So these two states are nothing but the equivalent. They are equivalent. Why? Because the output is stating as 0 as 1. See here. If you observe 0 and 1 from S2 to S0, same. And from 0 to 1 from S3 to S0. 0 to 1 from S3 to S0 is same. So we are calling these two as the equivalent states. Okay. So now what we need to do, we are replacing S3 and S2 by single state. And now we are replacing it with the single state. So we got S0, S1, S2. And we are replacing S2 and S3 by single state. S2 and S3 by single state. Okay. So previously we had S2, right? S0, S1, S2, S3. See, S0, S1, S2, S3. This is what we have previous. But now, as we have observed that these two states are S2 and S3 are equivalent, what am I doing is, I am just omitting S3. Omitting S3. So, with these three states, now I can move forward. So, replacing S3 and S2 by single state in the state diagram. All the inputs and outputs with respect to all the states are same. Only thing that I did is I have just omitted, okay, this state. Why? Because S2 and S3 are equivalent circuits. And then finally, examining the new diagram, now the states S0, S1. What happens now? Now both S1 and S2 are replaced by single state. S0, S1, right? And now these two are equivalent. And now when these two are equivalent, see, if you observe from S1 to S2, my input is 1 and output is 0. And from S1 to S2, we see from S0 to S1, I can see input is 1 and output is 0. So when these two are 0, I can say that one of the state I can omit. So as these two are equivalent, okay. So see, if you observe from S1 to S0, I see 0 is to 1. And from S1 to S0, one put I can see 0, 1 as the input and output. Input and output. When these both are same, I can omit one of the state. So I am omitting this state S2. And finally, I will be left out with S0 and S1. So this is what I have left out. Why? Because my states S1 and S2 are equivalent to each other. Then S0, S1, same. Their outputs for the input 0 is 1. So when the input is 1, the output is 0, right? Here when the input is 1, the output is 0. Isn't it? So the next state for input 0. This is the input and this is the output. This is my input and this is for output. So when my inputs are 0, that is when it is 0, what happens? S0 is being in the same state S0. And when my input is 0, what happens? The transition from S1 is taking place to S0. And in the other case, when my inputs are 1, when the input are 1, the transition takes place from S0 to S1. And when the input is 1, the same S1 is taking its own transition in being in the same state. So the next state of input 0 is S0, input 0 is S0, and for input 1 is S2. Okay, input 1 is S2. Then, so this is about the equivalent state. In the exam point of view, if you are getting anywhere any question regarding the equivalent circuit, you have to draw the diagram based on the truth table and you have to see the possibilities, okay, based on the input and as well as the output. If you are seeing any similarity with respect to the input and the output, okay, if you see any similarity, that means what? If you see any response with respect to the input sequence, which if it is identical with the output sequence, then that is nothing but the equivalent state. If you are finding two states are to be equal, then you can make those two states as one and then you can move forward. Finally, with respect to the two states S1 and S2, you can make a truth table and write down the next state outputs and the present state with respect to x is equals to 0 and x is equals to 1. So this is all about the sequential circuit, sequential machines, synchronous sequential machines. So this kind of examples we can see more in the examples like Mealy and more examples. So this is all about the sequential circuits. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.